Alright, let's get started on this first one. Take the limit as x approaches 0 of this guy. Okay, so if you remember, whenever we do limits, the first thing you try is you try to substitute in the 0 or the number that the x value that you're approaching. And when we do that, we can see that we're going to get 0 over to 0, and that is an indeterminate form. So whenever we have an indeterminate form, like 0 over 0, we can use L'Hopital's rule, where all we need to do is take the derivative of the top and take the derivative of the bottom, and then do the limit again. So if I take the derivative of the top, I get 3x squared minus 1. On the bottom, I get 3x squared minus 4. Now when I plug in 0, this will cancel out and this will cancel out, and I'll be left with negative 1 over negative 4. So my answer is 1/4. If you don't want to use L'Hopital's rule, of course, there is another way to do this one, and that's algebraically. If we were to factor out an x out of the top, the numerator, and an x out of the bottom, these would cancel out, and then you would take the limit of that. And that should look familiar. It almost looks like this, except there's a 3 right here. But you end up getting the same thing when you plug the 0 into these x squareds. They just go away, and you're left with negative 1 over negative 4. That's the answer for that one, 1 over 4. The next one says find the zeros. Don't forget, zeros also means x-intercepts. We're just trying to find the x-intercepts of this. So in order to find the x-intercepts of that, we take it and we set it equal to 0. And of course, there's different ways to think of this. You could make 0 over 1 and then cross multiply, where you just go this times that equals this times that, and this would go away. Or, I guess a normal way that I think about it is I multiply both sides by the denominator so that it looks like this. And this would cancel out with that. And I multiply 0 by that, blah, blah, blah. And it doesn't matter what I write over there because I just get 0. So now I have x to the third minus x, and then so I factor out an x to get x times x squared minus 1. That's going to equal 0, and I use the 0 property now. I set x equal to 0, and I set x squared minus 1 equal to 0, and this one's already solved, and this one over here I'm going to get x squared equals positive 1, which would be x equals plus or minus 1. So positive and negative 1. So we have 3 zeros. But on a second look at these zeros, and this, you might not notice this right away, but you see that 0 right there? We can't have a 0 on the denominator. And if I plug that 0 into this, I'm going to get an undefined number, an undefined result. Which is why what some people do is they don't work with this guy. Instead, they work with x squared minus 1 over x squared minus 4, because this is a simplified version of that. But the problem with this is that you're not going to, like if you were to graph this, you're not going to get the hole in the graph like you would on this one. See, this one has a hole at 0. Because the 0 would make the denominator equal to 0, and you can never, ever, ever divide by 0. Even if you get a 0 on the top, 0 divided by 0 can happen. So this is not an x-intercept. Can't be. The function is undefined at that point. Alright, so we got our zeros, positive and negative 1. Next, let's look at C. C says, write an equation for each vertical and each horizontal asymptote. Now, if you found the zeros and you got this, hopefully after you do this question, you would see that 0 can't be an x-intercept. Because what you would do to find the vertical and horizontal asymptotes would be, first, you would take the vertical, to find the vertical, you would go and you would set the denominator equal to 0. So let's set x to the third minus 4x equals 0. You would factor out an x, you would get x squared minus 4. And then you get, let's see, x, and then you factor this some more because it's a difference of squares. X minus 2, x plus 2, Or you could have just set it equal to 0. You'll end up getting the same thing. I get x equals 0, positive 2, and negative 2. And this should have thrown up an alarm at you. Like, what? That's a vertical asymptote? And then you would have looked at this x-intercept and said, well, that can't be an x-intercept because 0 is a vertical asymptote. But then wait a second, that actually contradicts what we found out in our very first thing that we did, this limit. This limit says that the y values for this function approach 1 over 4. And if there is a vertical asymptote at 0, it would look like this, with the vertical asymptote like this. And normally lines go like that, or they go like that when they approach an asymptote. But this right here says, what we found out right here is that this function approaches 1/4 as we approach 0 from the left and from the right. So let's say this would be 1/4. The function should be going wha-bam, straight at it. However, that function should have a hole right in the middle, because we know that this function is undefined at 0. Remember, we plug the 0 into this, we get undefined. Ooh, that's weird. Okay, so we have two asymptotes, one at 2 and one at negative 2. I'm going to go ahead and graph those on this. And I'm going to cross the 0 out so that whoever's grading my FRQ knows that I don't think x equals 0 is a vertical asymptote. There you have it, negative 2 and positive 2. The next thing I would have to find are the horizontal asymptotes. Now, there's two ways to find horizontal asymptotes. You could use limits. You could take the limit of this as you approach negative infinity or positive infinity. But I do prefer the algebra way of doing things. To find horizontal asymptotes in algebra, you just need to know the degree on the top, which is 3, and the degree on the bottom, which is 3. And since both the degrees are equal, you take the leading coefficients of each of those polynomials, the top and the bottom, and then you put them over each other. So in this case, it would be 1 over 1. And so we have y equals 1 for my horizontal asymptote. So I'm going to put horizontal asymptote right there. Now remember the rules with asymptotes. Curves are attracted to asymptotes. So that means as you go and draw your curve, your line should be getting closer and closer and closer to the asymptote, in whichever direction you're going. But it'll never cross over that asymptote. Well, actually, that's a lie. It'll never cross over the vertical asymptotes. Sometimes this horizontal asymptote gets crossed over. But the other rule still applies. The curve is attracted to that asymptote. All right, so describe the symmetry of the graph of f. So to do that, all we need to do is we need to take f and we need to plug in negative x. This is D. All right, so let's plug in negative x and see what we get. If I plug in negative x, I get negative x raised to the third power. And then I'm plugging in negative x to the other one. You could probably also do this with this one. Yeah, it does work with that one too. And then, let's see, we got negative x raised to the third power in the bottom. Then we're multiplying that by negative x. All right, let's see what we get. This, starting from the top left, we're going to get negative x to the third, and then we're going to get positive x. Then on the bottom, we're going to get negative x to the third, and then we're going to get positive 4x. Oh, yeah. Check that out. That's exactly the same as what we started with. You see, if I were to take out a negative from the top and take out a negative from the bottom, these negatives would cancel each other out. And this result is exactly the same as what we started with. And so the rule says that if you were to plug in negative x and you got the same thing as you started with, like we plugged in negative x to this and we still got this, then that means we have symmetry about the y-axis. So I'm going to write sim y-axis. Last but not least, we're supposed to use all this information that we found and sketch the graph of f on the axes provided. Okay, so what we got to do first is, let's start on this left side right here. All we got to do is pick a number right here and see if we're going to be graphing it above or below, because we are just sketching. It doesn't have to be perfect. Yeah, it says sketch a graph. So Let's pick -3. So if I plug -3 into this, let's see what we get. Let's plug -3 in right here. You can use this guy too, but I'm just going to use this one. All right, -3 squared is going to be 9 minus 1. And then -3 squared is going to be 9 again. Then we're going to minus 4. What's that going to equal? Let's see, we got 8 on top, and on the bottom we have 5. That is the same as 1 3/5. So at -3, we're going to get 1 3/5, which is above our horizontal axis. And so I have to assume that we're going like this. Okay, now we got the middle part. The middle part can do lots of things. On the left side, at the beginning part, we could have done this, or we could have done this. But because we got 1 3/5, we knew that we were above the horizontal axis. Now, this graph can go like this, or it can go like this, or it can go like this, or maybe even like that. I don't know. But I do know that I have x-intercepts right there and there. Oh, snap. I also know that we have a hole right there. Oh, that kind of defines our graph for us. So we know that we're going to go like this. Perfect. And because this graph is symmetrical about the y-axis, I know for sure that this is correct. It does not end up going like this. And because we have this, we know that we have this, because we're symmetrical about the y-axis. And that's how you graph it.